Okay, so hello everyone. My name is Mohr. I'm working for Red Hat, and today I want to tell you a little bit about the cluster autoscaler for Kubernetes and how you can use it on the public cloud and how you can use it for your private cloud with the help of KubeVirt, which is a virtualization add-on for Kubernetes, which basically allows you to run virtual machines side by side with the ports on Bare-Metal, OpenShift, or Kubernetes installations. So in order to understand why we need the cluster autoscaler, I want to go with you through 4 main questions. First, how public clouds in general help you with scaling your application at all. How Kubernetes fits there in the picture and how it helps you to get out of more of your resources which you are buying on the public cloud. Then we will finally see why we actually need the cluster autoscaler. So we will ask the question how the autoscaler helps us with combining the public cloud and Kubernetes. And finally, I want to tell you a little bit about KubeVirt and the cluster autoscaler and how it can help you to deploy isolated workloads on your bare-metal cluster. So when we look at the first question, how the public cloud helps you with scaling, in general, the overall answer is pretty easy. It gives you virtual machines. It gives you a lot of them, basically as much as you need. You just have to pay. That's how it starts. So you have to make your application scalable to make use of that. And you typically do that with a simple application by taking the resource incentive parts of your application, put them in, and make them scalable, which means that they can run in parallel, put a load balancer in front of these parts, and when your nodes get under pressure, you scale up. When the pressure is gone, because no one is visiting for your web page or whatever, you scale down again. In theory, if you have a public API to be a cloud provider, you can just script everything, monitor your virtual machines, create new virtual machines, stop old ones. But typically, public cloud providers help you there a little bit. For instance, the Amazon Web Services, EC2, they have the autoscaling groups concept, which means that you can define a virtual machine template and assign scaling policies to it. Some typical scaling policies would be track a specific CPU metric, and if a trigger is activated, it scales up, and if another trigger is activated, it scales down. Google Compute Engine has pretty much the same thing. There it's called managed instance groups, and 2 typical scaling policies you have there are also based on metrics or, for instance, on load balancer requests. Let's now suppose we have our application running and it consists of 2 nodes right now where the load is higher than 80%. 80% triggers a scaling request inside the public cloud. So you get another instance automatically, and after you have 3 instances, the overall pressure drops to less than 80%, and everyone is happy again. But now we're in an interesting situation, because when you add more and more applications there, and you're working for a huge company where a lot of people are trying to go to the cloud, you see that there are a lot of resources, also here you see it already, which you are paying for, but which you're not using. So when we look again on the example with the 3 running nodes, you already see all 3 of them just have 65% of CPU usage, which means that if 100% is the amount which a full node has, you already pay for 105% node resources, which you are not using. So it's tempting to try to pack the workload tighter inside the VM, but that's actually not very easy to do. You would need an extra scheduler which helps you doing that. And also, if you want to share your machines with other people, so that they can also you make use of the leftover resources, you would need some kind of multi-tenancy or so on, which is normally not there in cloud. So you just have this basic workload unit, and you can't split it into further details. And that is exactly where Kubernetes can help you. Because Kubernetes is multi-tenancy, includes multi-tenancy support. It has a scheduler which can decide on its own where it's best to put your workload, where still something is left on the node. And It even has benefits when you think about creating applications, because you can define everything much more natural in the terms of how your application fits together, and less about, so you're basically describing much more how your application looks like, and much less how much of the public cloud resources you need. So the solution here is to just deploy Kubernetes inside your nodes on the public cloud, and then schedule everything with pods and containers. And that's what you also see here in the picture. So the outside is the Amazon Web Services or the Google Compute Engine node. And on there, you run your Kubernetes nodes. And in there, your workloads are finally running. So a fine solution. So you take your simple web application again. You put it into containers, make sure that it consists of microservices or whatever. And you're done. And then finally, you get some load on your web application, and it doesn't scale anymore. Because now, the autoscaler functionalities from the public clouds don't work anymore. Let's just consider a very simple example. We still have the three backends running with a CPU usage of 65% each, and you want to schedule a new pod which needs 50% of one node. We don't have that left anywhere. And so the Kubernetes scheduler tells you, oh, I can't schedule this, but the Google Compute Engine autoscaling group says, hey, I'm fine. There is no pressure on the node, so I will not scale up. And that is exactly where the autoscaler, sorry, wrong button, where the autoscaler finally helps you. It's just a small application which you can deploy inside your Kubernetes cluster. It's in principle agnostic to the cloud provider, so you can use it for Google Compute Engine, EC2, Azure. And it makes use of the autoscaling primitives which the public clouds offer you. For instance, as I've already said, the autoscaling group or the managed instance group. What it does in detail is it just monitors your Kubernetes cluster and checks if there are any pods which are not schedulable. And if it detects one, it looks on its node templates it knows about, tries to find out if the workload would fit there, and if yes, it tells the public cloud below to spin up a new VM. Then it gives the VM some time to register itself as a Kubernetes node. Once the resource pressure is not given anymore, it will just scale down the nodes. And that's pretty much it already. One side note here is that this is really just about this use case. It's not about pod autoscaling. There are extra pod autoscaler. And it's also not about load balancing regarding to descheduling pods, for instance, from one node and putting it to another node. There are also other projects which are doing that, for instance, the descheduler. In order to determine if a new workload really fits into a new node the autoscaler would create, the autoscaler needs to know a little bit about the node it would create if it creates a new instance. And typical metrics it needs there are how many CPU, how much memory, and how much storage the new node will have. Are there taints or tolerances on that node? Which labels are in the node? That are all metrics and informations related for the Kubernetes scheduler so that it knows if a pod would fit there. And below there, you see a typical YAML file of a node which contains a few fields which influence the decision. In the metadata, you have the label section, in this case with just one label, kubernetes.do/hostname. And you see the capacity of the node, CPU, memory, pods, stuff like that. And that's it. Now your application works again. It can scale up and down again. If you want to use it with Oberth or OpenStack, you're right now out of luck. It just supports public clouds at the moment. And now I created a backend for KubeVirt. And that offers very interesting use cases. In practice, this works like this. You have a Bare-Metal Kubernetes or OpenShift cluster with KubeVirt installed. And in there, you're now creating a nested Kubernetes cluster and tell the cluster autoscaler to monitor the nested Kubernetes cluster if there are shortages in the pods scheduling. And if it sees shortcomings, it talks to the Bare-Metal Kubernetes cluster and tells it to spin up another VM so that enough resources are becoming available again. In order to make that possible in KubeVirt, we had to think about also in implementing something like the cluster autoscaling group or the managed instance group for us. And we decided to create a virtual machine replica set. And the name is not chosen by instant. It really is pretty much the same like a replica set for pods, just that it creates virtual machines instead of pods. We need a little bit of metadata there so that the autoscaler has all the information to scale up. For instance, a label to allow selecting it as a node, so that the autoscaler knows that this will create nodes which will register to the cluster. You need a few annotations which tell it how much resources will be able to run, or how much pods will be able to run on that node, how much storage will be there. And below that, in the spec section, you see replicas 3 in this case, which means create 3 VMs or make sure that 3 VMs are running. And that's pretty much then what the cluster autoscaler will manipulate during the runtime to scale up and down virtual machines. But that's not all what you see here. There is, on the second screen, the specification goes on. And here you see the actual specification of the virtual machine it will create. As you can see, you can specify resources on the virtual machine, how much memory it will have, how much CPU cores it will have. You can add disks there. And what you see here is that I've added 2 disks. The first disk, the boot disk, references the boot disk volume in the volume section below. And this is just referencing a Fedora 27 image. And we have a second disk here, which is a cloud in and no cloud data source, which we can use for bootstrapping the node and auto-registering. It references just the plain Kubernetes secret, which contains the bash script in this case. Such a bash script could, for instance, look like this. This installs Docker, kubeadm, and Kubernetes client. kubeadm is a very nice tool for bootstrapping automatically bootstrapping secured Kubernetes clusters. And then you start Docker and kubelab, and then you just invoke kubeadm join so that it can register itself to the cluster. And the final step which you need is you need to configure the cluster autoscaler so that it can talk to all Kubernetes instances. You create a very simple config file which points it to the configuration file of the Bare-Metal Kubernetes cluster. And then you start it, point it via --kubeconfig to the nested Kubernetes config. Via --cloud provider, you select the KubeVirt backend. Via cloud config, you point it to the init file I've written here on the top of the page. And node group auto discovery is now the part where the labels from before on the virtual machine replica set gets interesting again. There I put the KubeVirt.io autoscaler label there. And here with that expression, we're telling the autoscaler that it should look for virtual machine replica sets with exactly that label. And as a selection strategy, which node template it should use, I'm using here least waste, which means it goes through all the node templates and just checks which one fits best the workload and leaves the least CPU and memory unused. And that's pretty much it. Now your bare-metal cluster will scale up or down. And I've already mentioned the first interesting use case, and that is what you're seeing here. You can have, like in the public cloud case, you can have a completely nested Kubernetes cluster which can scale up and down by asking for more resources by the bare-metal Kubernetes installation at the bottom. And that's kind of the typical public cloud multi-tenancy use case. You don't have to take care of what the customer is doing in there that much. I mean, you of course need to secure network and everything, but it's completely separated from the bare-metal resources, and the customer can do there whatever he wants. But there is also another use case, and that is now about isolated workloads. Because here, we're not creating a nested Kubernetes cluster. Instead of that, we're telling the cluster autoscaler that it should monitor and scale on the same cluster. So it it can check on the bare-metal cluster if there are unschedulable pods with a specific label like needs isolation. And if such a pod is not schedulable anymore, it asks the same bare-metal Kubernetes cluster to spin up a virtual machine, which registers a node on the bare-metal installation. So you basically have two different types of nodes, the bare-metal nodes and the virtualized nodes. And in the virtualized nodes, you can then run isolated workloads. A typical example for that is, for instance, if you want to do CI for GitHub. In GitHub, it's typical on every pull request, you run some tests. But what's run there is pretty much opaque for the CI system. You just execute arbitrary code there. You have no idea what people are doing there. So you probably make sure that you don't schedule such workloads directly next to your sensitive, high-performance pods on the bare-metal node. So you want to isolate them. And this is exactly where this scenario can help you. If you want to go into the details there a little bit more, you can read about the cluster autoscaler in their GitHub repo. There's a pod autoscaler too, which I've mentioned, and a descheduler. These three projects kind of make a whole story out of the whole scaling in the cluster. You can also see where the KubeVirt related resources for the cluster autoscaler are located. And if you're interested, you can also read about the GCE and EC2 scaling groups and learn more about them there. And that's already it. So, are there some questions? Please.
Does this technique also work on the public cloud?
So the question was if the technique also works on the public cloud, and not with KubeVirt, if that is the question, since KubeVirt requires nested virtualization enabled. But of course, you can just install as said before, you can just install the autoscaler directly in the public cloud, and you have the same effect like in the first use case with the nested Kubernetes cluster. But that's not related to KubeVirt. Okay, no further questions, then thank you very much.